Alright, so in this next section we're going to take a look at the first types of lipids that are saponifiable. Which means that they contain ester bonds. The first ones we're going to take a look at are the simplest ones, which are called the waxes. And what a wax is, it's an ester, right? So it contains our C double bond O, and specifically it's an ester of a saturated fatty acid, so a long carbon chain, carboxylic acid, and also a long carbon chain alcohol, right, where each of these contain anywhere from 14 to 30 carbon atoms. What that means is, right, your wax is going to contain lots of carbons and H's, right, which would make it very nonpolar, or highly nonpolar would be a better term. Right, which again means that it would be water insoluble. It's not going to dissolve in water. And if you think about where you use waxes, for instance, to protect your car, right, it just repels the water. So a wax would contain an ester bond, that's this region here, that links a long chain carboxylic acid, a fatty acid, to a long chain alcohol. So for example, you can have something like beeswax that looks like this, right? So there's a CH3 and then there's 14 CH2s connected to that carbon. So there's a total of 14, 15, 16 carbons on this side. And then on the alcohol side, there's 29 carbons here, plus one, there's 30 carbons on that side. Right, so it's a huge molecule, relatively speaking, made up mostly of C's and H's, very, very, very nonpolar. Extremely nonpolar. What makes all of these similar, again, is the fact that they all contain that ester bond, right? That's your link here between the acid and the alcohol. The next class of compounds are known as the Triacylglycerols, or triglycerides, right? They both mean the same thing. Or sometimes you'll see the term triesters. Because guess what? They all are going to contain three ester groups. And these are esters of a particular alcohol known as glycerol. And glycerol is also known as glycerin. And the alcohol groups, the OH groups from glycerol, are able to form esters with three fatty acids, right? So glycerol or glycerin looks like this. There's 1, 2, 3 carbons. And then there are 3 alcohol groups. Right, so if you were to name glycerol, and the IUPAC name, it would be 1, 2, 3 propane triol. Right, that would be the IUPAC name for it, but it's more commonly known as glycerol. So these alcohol groups here can react with carboxylic acids groups from three fatty acids to make your triacylglycerol, or your triglyceride, or your triester. All right, so the way that we name our triacylglycerols or triglycerides is we change the first name from glycerol to glyceryl, just like we would any other ester. And then the last name, right, depends on the carboxylic acid. So if we're starting with stearic acid, that becomes stearate. And then because we have 3 of these, right, we toss the tri in there. So glyceryl tristearate would be the name for that triacylglycerol that's formed from glycerol and 3 stearic acid molecules that's shown down here. So this is our glycerol, right? Our 3 carbon alcohol right each bond or hydroxyl groups. And then if this is my first fatty acid, right, which is stearic acid, the OH from the fatty acid and the H from the glycerol can combine. And if I have another stearic acid coming in, the same thing can occur with those, and a third one coming in can combine in the same way. So we end up producing 3 of those water molecules, and the new bonds that we've made now are these ester bonds, which look really, really similar. They're actually the exact same bond we saw back in the esters chapter, right? So if you were to, again, look closely at this, this is going to be your glycerol backbone over here, your 3-carbon backbone. These are all your ester bonds. And then the other part of it, and I know it's not, you can't necessarily see it here, but we'll expand the structure out just to make it look a little more obvious. So we have our CH2 connected to a CH and another CH2 underneath. There's your ester bond. And then to these we have 16 and 17 carbons, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right, so that's how the structure would look if you were to expand it out. Right here they just condensed the structures to represent 16 CH2s. We just drew it out here to actually show you in a better representation of the structure. So those that's how generally how your triacylglycerols are going to form. Sometimes your triacylglycerols are going to contain several different types of fatty acids, in which case we call them mixed triacylglycerols. So here, for example, we can have a stearic acid, we can have an oleic acid, we can have a palmitic acid. So these are all different fatty acids, but they're all still connected by the ester bond to the glycerol backbone, right? So because we have different fatty acids, we call it a mixed triacylglycerol. The triacylglycerols or the triglycerides are really the major energy form or the major energy storage that we have in animals, right? Specifically animals that hibernate. You know, they lower their activity levels in the wintertime. They eat huge amounts of things that are high in calories to store that energy for use when they're hibernating. All right, so let's take a look here at how we can draw the structure of a couple things. So let's go down to the very last one down here. All right, so it says draw the condensed structure for the triacylglycerol containing 3 molecules of myristic acid, and it tells you myristic acid has 14 carbons and there's no double bonds in it, right? That's what the notation says. So we're going to start with the glycerol backbone. We have our C, C, and C. We have our H's. Right, and then all we're going to do is to draw that ester bond. So there's our O connected to a C double bond O. And then we have 14 carbons in each of these. So this C double bond O here counts as 1. So we have 13 more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right, those are your 14 carbons, and they're all the same. Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 1, 2. So that'll be your structure for the triacylglycerol formed from your glycerol backbone, which is this part of it, and your 3 myristic acids. And then in green here is going to be your ester, links between those components. And if you were to condense the structure down, right, this is what you'll see as the notation that's used. So based on the type of fatty acids you have in your triacylglycerol will dictate whether you're dealing with a fat or whether you're dealing with an oil. All right, so fats are usually solids at room temp, right, which means that they generally have higher melting points. And your fats usually come from animal sources like meat, etc. Whereas your oils tend to be liquids at room temperature, so they're going to have lower melting points than your fats. And they usually come from some sort of a plant source, and that can vary, right? So your oils coming from your olive and peanut oil, they tend to be monounsaturated. They're going to contain large amounts of oleic acid. And remember, when you have your unsaturated fatty acids, right, these are not going to pack. So they do not pack close together. So they're more spread out. So they're going to be more liquid-like. Whereas your saturated fatty acids tend to have higher melting points, and you usually find them in animal fats and sometimes in your coconut and palm oils. So if you were to just take a look generally at the relative amounts of each of the types of fatty acids that you find in different fats and oils, it's going to make a whole lot of sense now based on what you observe and what you see, right? So if you take a look at your let's say beef tallow or butter or coconut oil, you'll see there's a huge percentage of the blue, and the blue here is the saturated fatty acids, right? So these all tend to be solids. Whereas the liquids, right, all contain large amounts of the monounsaturated and the polyunsaturated fatty acids. So that's like your olive oil, canola, soybean, sunflower, corn oil. These all tend to be liquids, right, because they have the double bonds in their tail that form those kinks that don't allow them to pack close together. So that has a huge impact on the physical state of that lipid, whether it's a solid or whether it is a liquid.